Hello learners, myself Balgopal Mahapatra, lecturer in physics, both Panchayat College, both. Today we will discuss physics of class 12 standard, and this lecture includes magnetism and matter. To begin with this chapter of magnetism and matter, we have to discuss magnet and its properties, current loop as a magnetic dipole and dipole moment, bar magnet and its dipole moment, Coulomb's law in magnetism, important terms in connection in magnetism or important terms in connection with magnetism, magnetic field due to a magnetic dipole, torque and work done on a magnetic dipole, terrestrial magnetism, elements of Earth's magnetic field, tangents law, properties of di, para and ferromagnetic substances, and Curie's law in magnetism. Let us start with what is magnetism. Magnetism is the phenomenon of attracting small pieces of magnetic substances like iron, nickel, cobalt, etc. So, we may say a body possessing the property of magnetism is called as a magnet. In other words, it is a substance which exhibits the properties of small pieces of iron or iron filings, you may say particles of iron towards it, then it will be called as a magnet. As for example, you take small pieces of iron or iron dust, or you may say iron filings, and if a substance has the property of attracting those iron filings, then we may say that substance as magnet. One more important thing here, magnet that we are discussing, it may be a natural magnet or it may be artificial magnet. We may take the example of different type of magnet like bar magnet, horseshoe magnet. Magnet may be named after its geometrical shape. If it is in the form of a bar, it is a bar magnet. And here you may say the magnet that is available in the nature, in the earth's crust, it may be called as your natural magnet. But if magnet is available artificially, magnet is made artificially, magnetism is induced in the substance artificially, then it may be called as artificial magnet. But every magnet has a pole, that is called magnetic pole. A magnetic pole is nothing but a region near the end of the magnet where it shows maximum magnetic characteristic. That means near about the magnetic pole, it shows magnetic properties, and its strength is called pole strength. It is measured in SI unit as ampere meter. In other words, SI unit of pole strength is ampere meter. And the region around a magnet in which it exerts force on other magnet and on objects made of iron, it is a magnetic field. So, magnetic field may also be defined as the modified space around a magnet within which its influence can be realized. Its influence means within that region only other magnetic substances can be attracted towards it, or here those substances will start moving towards that substance. Now, what are the properties of a magnet? A freely suspended magnet aligns itself along north-south direction. That is to say, when you take a bar magnet, suspend it freely, it comes to rest with its north pole pointing north. So, a magnet has two poles. One is north pole or north seeking pole, other is south pole or south seeking pole. And two unlike poles, you say two, one north pole and the other south pole, we may say these are unlike or dissimilar poles. So, two unlike poles attract each other, whereas like poles repel each other. Means two north pole will repel each other and two south pole they will generally attract each other. Okay. And magnetic poles magnetic poles exist in pairs. We cannot get isolated poles. In other words, poles cannot be separated. If you take a magnet, go on cutting it again and again till you reach the atomic stage. That means if a magnet is cut and cut and cut, you repeat it again and again till you get a small particle, that is an atom, then an atom will also behave as a magnet. It will have a north pole, it will have a south pole. By cutting a magnet at its center, you cannot get north pole or south pole separately. That is to say, again it becomes two magnets. So, magnets always, magnetic poles always exist in pairs. Number 4, a magnet can induce magnetism in other magnetic substances. If you take an alpine small needle, rub it against a magnet, then the needle or alpine, it becomes a magnet again. So, we may say magnetism is induced in it. And the last property is that any magnet has the capability of attracting magnetic substances. So, whatever the attractive property it has, repulsion is the surest test of magnetization. A magnet can be identified surely with 100% accuracy if it repels. Generally, we know magnet attracts iron rod as well as opposite pole of the other magnet. So, it is not a sure test of magnetization. It is not at all a sure test of magnetization. But if a rod is repelled with a strong force by a magnet, then that rod is surely magnetized. Again I am repeating, if it is repelled, then we may say it is magnetized. So, every magnet has a magnetic field all around it, and that magnetic field may be, we say, uniform or non-uniform. Uniform field is a field which has same magnitude and direction at every point, whereas a non-uniform field is a field whose magnitude and direction do not remain same at every point. And any uniform magnetic field, here it can be represented by parallel lines of force. You may see to the figure, here lines of force are parallel and they are separated by equal distance. So, this represents a uniform field. This uniform field, it is in the plane of the diagram as is clear from the figure. So, uniform field is represented by lines of force. These are called lines of force. Lines of force gives direction of magnetic field. Remember, lines of force may be straight or curved. If it is a curve, then the tangent at any point of that curve will give the direction of lines of force. And direction of lines of force, magnetic lines of force, I do mean, it is always from north pole to south pole. And here any uniform magnetic field is represented by parallel lines of force which is separated by equal distance. Also, we may represent it by cross symbol. This is, you see, uniform field perpendicular and directed into the plane of the diagram, represented by this cross. Again, here you see it is represented by the dot where the field is perpendicular, but it is going out of the plane. In the red figure marked with red ink, it is directed into the plane of the paper, whereas in the pink color dot representing uniform field, they are representing field which are perpendicular but emerging out of the plane of the diagram. And experimentally as well as mathematically, it is established that current loop can behave like a magnetic dipole. So, now we will discuss current loop as a magnetic dipole and dipole moment. Any current carrying conductor is associated with a magnetic field as per Oersted magnetic effect of current. You see, this is a current carrying loop, current flowing through it in anticlockwise direction. You see here a magnetic field will be developed all around it, whose direction is as represented in the figure, and we can establish also mathematically that it can behave like a magnetic dipole. Why? We can see its magnetic dipole moment can be derived to be vector m equal to I into A into n cap. I is the current here, A is the area of cross section here, and n cap gives the direction of magnetic dipole moment. magnetic dipole moment, it is a vector quantity directed from south pole to north pole. And here its SI unit of magnetic dipole moment, it is ampere meter square. How it becomes ampere meter square? Here you see magnitude of magnetic dipole moment, it is the product of current and area. SI unit of current is ampere denoted by A. SI unit of area is meter square denoted by m square. So, H magnetic moment is ampere meter square. It is associated with a circular current carrying loop. We may say definitely a current loop behaves like a magnetic field, and when we look at any one side of the loop carrying current, if the current is in anticlockwise direction, then that side of the loop behaves like magnetic north pole. But if current is in clockwise direction, then that side of the pole will behave like south pole, which is very clear from the figure. Now, let us discuss about a bar magnet. Here you see it is a bar magnet. What will be the magnetic field due to a bar magnet? That we will find out. Here you see the pole just remains inside the face, not exactly on the face of the magnet. It just remains inside the face marked by P on the figure, and on the right hand side here you see north pole is there, and again south pole is there here. Both poles are represented by P and P, and magnetic moment here you see represented by putting a vector symbol over M. Vector M, it is directed from south pole to north pole. One important thing, the distance between the south pole and north pole, that is face to face distance I am talking about. The distance between south pole and north pole and face to face distance of a bar magnet are not same. The face to face distance, it is called as magnetic length, whereas the face to face distance, it is called as geometric length, whereas the pole to pole distance, south pole to north pole, two dots are marked in yellow color. Here you see the spacing between them will be magnetic length, whereas the face to face distance, it is called as geometric length. One more important thing, the line joining the poles of the magnet, it is called magnetic axis. The line joining poles of the magnet, it is called magnetic axis, and that pole to pole distance, again I am repeating, it is called magnetic length. In other words, the distance between the poles of the magnet is called magnetic length of the magnet, whereas the distance between the ends of the magnet, it is called geometric length of the magnet, and always geometric length is greater than magnetic length, or if you find out the ratio of magnetic length to geometrical length, it will be about 0.84 times. And this magnetic dipole, you see, it is nothing but, what is a magnetic dipole? That is our point of discussion. Any pair of magnetic poles of equal and opposite strengths, means one will be north pole and the other will be south pole, and separated by a finite distance, very small distance, that is called a magnetic dipole. So, we may say magnetic dipole, it is a combination of two opposite poles of equal strength separated by a very small distance, which is finite, one north pole, another south pole, very close to each other. And the magnitude of dipole moment, it is the product of pole strength small m and the separation 2L between the two poles. It is a vector quantity directed from south pole to north pole. You see, it expression is vector capital M will be small m into 2L into L, a I cap you may take, which will give the direction of the magnetic dipole moment. And here, as it is product of pole strength and distance, here its SI unit will be ampere. Pole strength, its SI unit is ampere meter, length it is meter. So, magnetic moment will have SI unit as ampere meter square. Okay. Next thing, here generally we see that the magnetic poles, if they are opposite pole, they attract each other. If they are similar poles, they repel each other, and generally the force of attraction or repulsion, we may say magnetic force between two magnetic poles, it is governed by Coulomb's law in magnetism. So what is Coulomb's law? Coulomb's law in magnetism states that the force of attraction or repulsion between two magnetic poles is directly proportional to the product of their pole strengths and inversely proportional to the square of the distance between the two pole strengths. Suppose you take two poles of strength M1 and M2 as is represented in the figure, separated by a distance of r, and as per Coulomb's law, F will be directly proportional to M1, it will be directly proportional to M2, we say F will be directly proportional to product of M1 and M2, and it is inversely proportional to r square. It is inversely proportional to r square. It is not proportional to, rather it is inversely proportional to r square. So F will be equal to K M1 M2 by r square. F will be equal to K M1 M2 by r square, where K is a constant of proportionality, and in SI value of K is mu 0 by 4 pi. You see, F will be equal to mu 0 by 4 pi M1 M2 by r square, where K equal to mu 0 by 4 pi is a constant. Mu 0 is called permeability of free space. Mu 0 is called permeability of free space or absolute permeability. Its value is 4 pi into 10 to the power minus 7 Tesla meter per ampere. Tesla meter, inverse means Tesla meter per ampere, and as force between, it is a vector quantity, force in vector form is represented as F equal to mu 0 by 4 pi M1 M2 by r square into r cap, where r cap is a vector directed along the spacing r, but unit vector r cap may be given as vector r by r, so it is represented in this way. Now, what is magnetic intensity or magnetizing force? Represented by symbol H. Magnetic intensity at a point is the force experienced by an earth pole of unit pole strength placed at that point due to pole strength of the given magnet. So, we may say it is the force experienced by a unit earth pole. So, if H is the magnetizing force, B is the magnetic induction, mu is the permeability of the medium, then B and H are related by the relation H equal to B by mu or B equal to mu H. Mu H is clearly told to you, it is magnetic permeability of the medium. Also, one may define magnetic intensity as the magnetomotive force per unit length. Alternatively, it may be defined as the degree or extent to which a magnetic field can magnetize a substance. Again, mathematically it can be derived quantitatively from this formula F equal to q b sin theta. F is the force, q is the charge, b is the velocity of the charged particle, b is the uniform field strength in which it is moving, and theta here it is the angle made by the charged particle with the direction of the magnetic field. So that F equal to q b sin theta, and from this expression, if the charge is moving perpendicular to the field, you say sin theta will be sin 90, it is 1, so F will be equal to q v. So if q is 1, v is 1, then F will be b, means force will be equal to your magnetic field strength. That's why it is defined as the force experienced by unit positive charge flowing with unit velocity in a direction normal to the magnetic field. Okay, but here we see the SI unit is ampere turns per linear meter. Whose SI unit? It is the SI unit of your magnetic intensity, and in CGS it is measured in oersted. Now let us discuss what is magnetic field strength or magnetic field or magnetic induction and magnetic flux density. Already we have discussed about magnetic field. Now what is magnetic flux density? Magnetic flux density, it is the number of magnetic lines of force passing normally through a unit area of the substance. It is also called as magnetic induction, B, represented by mu h, that is B equal to mu h. Its SI unit is Weber per meter square, or it is called as Tesla, but CGS unit is Gus. We can establish the relation that 1 Tesla equal to 10 to the power 4 Gus, or 1 Gus equal to 10 to the power minus 4 Tesla. Okay. Now, what is magnetic flux? Phi. It is defined as the number of magnetic lines of force passing perpendicular through the surface. It is the number of line of force crossing normal to the surface, and it is measured in SI in Weber, after the name of scientist Weber. And already we know the relation between magnetic induction and magnetic intensity is B equal to mu h. Mu is the permeability of the medium, that is magnetic permeability. And magnetic permeability, what is it? It is the degree or extent to which magnetic lines of force can pass or enter a substance. So, it gives idea about the degree of magnetization. Permeability gives idea about the degree of magnetization. In SI, it is measured in Tesla meter per ampere or Weber per ampere per meter. And correspondingly, we will discuss now another quantity, that is relative magnetic permeability, denoted by mu r. R is the subscript here. What is it? The word relative suggests definitely magnetic permeability of one substance will be compared with the standard value of the other, and standard value of the permeability will be taken as that of free space or vacuum. So, relative permeability, it is the ratio of magnetic flux density in a material to the magnetic flux density in vacuum. Also, it is defined as the ratio of absolute permeability of the material to that of the vacuum. Absolute permeability, if it is mu O by mu 0 or mu 0, and your for vacuum it is mu 0 and for the material it is mu, then mu r will be equal to mu division mu 0. But if we take magnetic flux density for a material is B and magnetic flux density for the same material in vacuum is B0, then relative permeability is B by B0. It is quite obvious from the formula. Now, let us define what is intensity of magnetization. Intensity of magnetization, it is the degree to which a substance is magnetized when placed in a magnetic field. It is the degree to which a substance is magnetized when placed in a magnetic field. It can also be defined as the magnetic dipole moment acquired per unit volume of the substance, that is I equal to m by v. I is here intensity of magnetization, m is magnetic dipole moment, v is the volume of the substance. So, I will be equal to m by v. And let us reduce this formula. Capital M, it will be small m into 2L. You see in point number 5 in V, I equal to small m into 2L, because magnetic moment m equal to small m into 2L, and volume V will be area into 2L, A into 2L. So, 2L gets cancelled. So, we get I as small m by A, pole strength per unit area. Therefore, intensity of magnetization may also be defined as the pole strength per unit cross sectional area of the substance. And you know, pole strength is measured in ampere meter, area is in meter square. So, ampere meter division meter square will yield how much? Ampere per meter. That is to say, SI unit of intensity of magnetization is ampere per meter. Now, one more term in connection with this magnetism chapter. What is magnetic susceptibility? Magnetic susceptibility is nothing but the property of the substance which shows how easily a substance can be magnetized. How easily a substance can be magnetized, that idea is given by susceptibility. Again, one may define susceptibility as the ratio of intensity of magnetization in a substance to the magnetic intensity H applied to that substance, that is I by H, capital I by H. So, it will, from the formula it is quite clear, susceptibility has no unit. But there exists a relation between magnetic permeability and susceptibility. We can establish this relation that mu r equal to 1 plus k. Mu r equal to 1 plus k. Here you see mu r is the magnetic permeability, k is the susceptibility. So, knowing susceptibility, you can calculate relative permeability. Suppose susceptibility is 21. What is permeability? 1 plus 21, 22. If a question is asked, relative permeability is given 22, calculate susceptibility, you substitute the formula, you use the formula, substitute the quantity given, out of mu r and k, 1 will be given. So, no problem in calculating the other. Next thing we will discuss, what is the magnetic field due to a magnetic dipole and a bar magnet. So, that magnetic field will be calculated at a point. That point may lie on the axial line of the magnet or on the equatorial line of the magnet. Here you see, this is a magnet, axial line is a line passing through the south north line, magnetic moment is directed from south to north. Suppose O is the center and distance between the center and one of the pole is L, that is to say 2L is the length of the bar magnet. You see the axial line, P is a point on the axial line marked in red color, and here suppose this point P, it is at a distance x from the center of the magnet, and if a unit north pole will be placed at P, to know what is its direction, it will be repelled by the north pole. That will give the direction of the magnetic field due to the north pole, that is represented as Bn in the figure. Similarly, that north pole will be attracted towards the south pole with a force represented by Bs, that is the magnetic field due to the south pole. And here you see both the north pole and south pole are oppositely directed. We can find out what is Bn, what is Bs. Bn will be greater than Bs, and the net field due to the point, due to the bar magnet at the point P, Bp will be equal to Bn minus Bs, and if you calculate the value of magnetic field at the point, axial point P, you may say point on the axial line, it is will be equal to mu 0 by 4 pi 2 mx division x square minus L square whole square. Remember, this axial line is also called as tan A position, tan A position or and on position of the magnet. But this distance small l, it is very less than x. So, L square will be still smaller, and from the denominator of this formula we can neglect L square. Therefore, it will be equal to mu 0 by 4 pi 2 mx by x4. After solving it, we will approximately get magnetic field on the axial point is mu 0 by 4 pi 2m by x cube. That is the expression. In a similar way, we will go for deriving what is the magnetic field at a point lying on the equatorial line. Equatorial line is the perpendicular bisector. It is OQ. It is OQ. It bisects the bar magnet into two equal halves. Q is at a distance y from the center. You see both the poles are situated at what distance? You know, ON or OS is L. You may apply Pythagoras theorem, so that each line QS or QN, it will be equal to square root of R square, square root of y square plus L square. And here the lines ON and OS are aligned at an angle theta with the axial line, and let us place a unit north pole at this point Q. So, it will experience a force along OQBN. So, magnetic field due to the north pole for equatorial point, that is Bn. Similarly, unit north pole placed at Q, it will be attracted towards S, giving field strength Bs due to south pole. You see how Bn and Bs are aligned at an angle theta with a line parallel to the axial line. So, taking Bn and Bs as two sides of a parallelogram, you may complete the parallelogram, so that applying parallelogram law of vector addition, resultant field direction may be also obtained if it represents a parallelogram, that will be BQ. That will be by subscript we may say BQ, it will be along QP. But directly we may find Bn and we may find Vs, find its component. The two horizontal component of Bn and Vs will act along Q BQ, and finally we may arrive at this formula: BQ will be equal to mu 0 by 4 pi m division y square plus L square whole to the power 3 by 2. But this L is very small as compared to y, so that L square can be neglected as compared to y, and finally neglecting L square we will get BQ, not BP, it is BQ as mu 0 by 4 pi m y square to the power 3 by 2, that is y cube. So, here BQ will be equal to mu 0 by 4 pi m by y cube. So, this is how we can find in this case that whenever we are finding magnetic field at a point on the axial line, it acts along the dipole moment vector, along the axial line. But when magnetic field at a point on the equatorial line is calculated, it acts opposite to the dipole moment vector. So, magnetic field at an axial point and at an equatorial point, these two are oppositely directed, these two are opposite to each other. So, this much today. See you next time. Thank you.